So welcome back to our next video on sequences. So suppose somebody just gives us a sequence and then we're asked to find an explicit formula for the nth term of the following sequence. So when they say an explicit formula, what they really mean is that in this case, our explicit formula really means we need a closed form for that sequence. And so how do we come up with something like that? Well, we kind of begin by looking at the sequence itself. So something that we notice here is that for our numerators, that we have numerators of 4, 16, 64, 256, 10, 24. So if we just look at the numerators, then we have 4, 16, 64, 256, 10, 24. Well, if I look at common ratios of those things, if I look at 16 divided by 4, I get 4. If I look at 64 divided by 16, again, I get 4. If I look at 256 divided by 64, again, I have 4. And finally, if I look at 1024 divided by 256, I once again get a value of 4. Okay? So what that's really telling me is that at least my numerators have some kind of recursive formula that the kth element is going to be the previous element times 4. Well, I recognize that as a geometric sequence. And so my corresponding closed form for that thing is then going to be my first element, 4, times my common ratio of 4 to the k minus 1 power, or just 4 to the k power. And that will work for k equal to 1, 2, 3, and so on. So I found a pattern for the numerators. Let's see if we can find a similar pattern for the denominators. Plus 5 gives me. So in the denominators, now I'm seeing, denominators. I'm really seeing a pattern of 5, 9, 13, 17, 21. Well, if I look at those and I kind of look at common differences, common consecutive differences, so if I look at 9 minus 5, I get 4. If I look at 13 minus 9, that also gives me 4. If I look at 17 minus 13, I get 4. And finally, if I look at 21 minus 17, one more time I get 4. So what this is kind of telling me is that d sub n, so if I use d for our denominators, so d sub n, if I look at the difference between two consecutive denominators, that I always get a value of 4. And so kind of put another way, d sub n is going to be d sub n minus 1 plus 4, and which I recognize as an arithmetic sequence, for which I then know what the closed form is. So the closed form is going to be my first element, which is 5, plus n minus 1 times my common difference of 4. So that if I kind of multiply this out, what I end up with is 4n a plus 1 out of that. And so I've kind of found a pattern in the denominators as well. And so let's kind of put this together and see if we can get a final description of this sequence. So for my numerators, I had sequences that look like, these guys look like consecutive powers of 4. For my denominators, they were my arithmetic sequence, and so I had 4k plus 1 for those guys. So that always worked for k greater than or equal to 1 in that case. K greater than or equal to 1. So if I kind of put these together, what does this sequence look like? My a sub n looks like my kth numerator divided by my kth denominator, or 4 to the k divided by 4k plus 1. So this almost gets me what I want. But one thing that I have missed so far is that these guys have an alternating pattern. So here I have a plus, then a minus, then a plus, then a minus, and then a plus. And so how do I compensate for that? Well, those are just alternating powers, and I compensate for that by looking at things like minus 1 to the n plus 1 powers. Since my first one is positive, I will take, so if n is 1, then I get minus 1 to the 1 plus 1, so minus 1 squared, and I get 1. So my first term is going to be positive. Okay, so this kind of tells me how I can start with this sequence. So if I put these together, what does my sequence look like as kind of this final answer? Well, as a final answer, my kth term then looks like a minus 1 to the k plus 1 times 4 to the k over 4k plus 1. And that will work for k greater than or equal to 1. So if we take a look at this sequence, then let's see if we can figure out what a formula is going to be for this. Okay. So again, kind of looking at starting at our index of 1, if we do the same thing and look at the numerators, so our numerators are really just going to be 1, 2, 3, 4, 5, 6, and so on and so on. And so pretty easy to see that our numerator is just going to be that the kth element of our numerator is just going to be, well, k. For our denominators, we have 7, 13, 19, 25, 31, and so on. Well, if we look at common differences there, 13 minus 7, we get 6. 19 minus 13, again, we get 6. 25 minus 19 is 6, as is 31 minus 25 is also going to be 6. And so this tells us that our kth denominator is going to be our previous denominator plus 6. Okay, so this gives us an arithmetic sequence and tells us that d sub k is then going to be our first element, so our first element was 7, plus k minus 1 times our common difference, 6. So if we kind of simplify this a little bit, we get something that looks like 6k plus 1 for our closed form. So again, in this one, what we have is that we have the alternating patterns in the signs. So our alternating patterns, we see positive first element, negative second element, positive third element, negative fourth element, positive fifth element, and so on. And so again, that kind of tells us, oh, I have some kind of minus 1 to some power, but then do I want my first element to be positive or negative? Well, since I want my first element to be positive for index 1, then I can either just add 1 or I can subtract 1, depending on what my index is. And so if I take minus 1 to the k plus 1 for my values, now I can actually get a formula for this sequence. So what does my kth element look like? Well, it looks like minus 1 to the k plus 1. That gets my signs all over my kth numerator divided by my kth denominator. So I get minus 1 to the k plus 1. My numerator, we said, was just going to be k. And our denominator looked like 6k plus 1 for our denominator. So our closed form solution for this thing is going to look like minus 1 to the k plus 1 times k over 6k plus 1. So here's been a couple of examples of how we can figure out what the formula for our sequence is going to be. I hope you've enjoyed this, and so I will see you guys for the next discussion.